This is the lesson plan for today. He was going to do some audio. He's going to start audio today, but he said that there's too much that he wanted to do. He can't get to the audio yet. So today we're just going to do this. Going to do the data blocks, some optimization, talk about weight decay, and some transforms. These are kind of like it seems to me they're like the crown jewels of the Fast.ai library that as it's coming together. And there's this, there's just these beautiful I don't know what you call them. They're like little mini modules that just make all the tasks of building a model and testing it and so on and bringing in the data. I think it's just so trivial. It's just really nice. So I decided to focus on since there was so much material, I decided to just focus on the notebooks that we're doing. And so I'll just go through it and say a little bit about each notebook, and that's how the lesson will go. So the first one, he uses this LSUV notebook, which is called Layer-Wise Sequential Unit Variance. And it's based on the paper, all you need is a good init. And the algorithm is laid out here on the left. You basically, instead of batch norm where you normalize at every step, in LSUV you just normalize first step. You just normalize the first batch, and then things just evolve to take care of themselves. The data takes care of itself from then on. So and the way you do it is for each layer, you check to see if the variance is within a certain tolerance of 1. If it's within the tolerance of 1, then you're good. Otherwise, you divide by the variance. You divide the weights by the variance by the square root of the variance, and that brings it in the next. That will bring it closer to a variance of 1. That's the key. So the way the authors say this is they say that LSUV is data-driven weights initialization, and it works on all. And the reason why they developed it is because there's all kinds of layers that people use in these convolutional networks and other kinds of networks, and you've already seen them. They include dropout layers and pooling layers and average pooling layers and so on. And for each one of these layers, you would have to derive a mathematical proof of. You'd have to derive a mathematical procedure for doing the initialization, which could get complicated. So they decided to do it by letting the data itself guide you to the initialization, and then their method is general. It works on any kind of a network, no matter how many different kinds of layers like dropout and pooling and so on that it includes. They are aiming, just as the batch normalization, they're aiming at state-of-the-art performance on thin and deep convolutional neural networks. Thin means that the number of nodes in each layer is relatively small, so it's not a wide network. I guess you'd call it a narrow and deep. And deep means that there's many different levels, up to 1,000. People in the literature, people talk about networks with up to 1,000 layers, and they're still getting to converge and perform well. So what it is that essentially LSUV is batch normalization of the layer outputs done only once before the start of training. For that reason, there's less computational overhead than if you do full batch normalization, so it saves you some compute time. They showed that, and they also showed this is something that's been batted back and forth in the forum about whether batch normalization should be done after the nonlinear activation or before. And in their paper, they showed some research. They did some small studies and showed that batch normalization is usually best done after the nonlinear activation function, which kind of makes sense to me, because the activation function can do some weird stuff to your weights, and after that it does that weird stuff, it changes their variance and mean, and so that's when it seems to me that that's when you'd want to do the normalization after the nonlinear activation function is applied rather than before. So the bottom line is their paper, they show that this layer-wise sequential unit variance achieves state-of-the-art performance on the MNIST data. That's the digits data set that is kind of like a favorite for all of these techniques to try them out on. Okay, so then the next notebook is notebook 8, which is the data block, and so he introduces he first talks about how, or Jeremy first talks about how he got this idea from a paper by Dmitro Mishkin, Nikolai, I think that's supposed to be Sergeyevsky, and Jiri Matas. What did I do? Did something I shouldn't have done. Yeah, and what they did was they picked smaller subsets of the ImageNet data set in order to accelerate the training, in order to be able to train faster. They use smaller image sizes and a smaller subset. Instead of taking the whole ImageNet of millions of images, they took subsets of it. And so Jeremy adopted that idea, and it allows you to do accelerated training, and it enables you to do a systematic study of network architectures for ImageNet. And that's what Jeremy's done, and that's what these guys did in this 2015 paper. I'm sorry about the typo. It's a 2015 paper, Systematic Evaluation of CNN Advances on ImageNet. So what Jeremy did was he built a two sort of toy data sets. One is image, he calls it ImageNet, ImageNet, something like that, French accent. And that one has something like 13,394 images out of the whole ImageNet data set, and they're 160 by 213, the 160 pixels by 213 pixels by 3 channels, and then normal RGB channels. And instead of having 1,000 classes like the ImageNet data has, he chose 10 classes, and I can't remember what he said. They're easy to distinguish, so he calls this the easy data set. And then he also built another toy data set called ImageWoof, which is meant to be a harder data set. Here he did a similar thing where he chose a subset of the images that had to do with dogs, and but they're similar. But the images are comprised of dogs that are from similar breeds, so that means they're hard to classify. And so this is like a hard data set, the ImageWoof data set. So having said that, he links to, there's a link to the page where he does all this stuff. There's a GitHub where he has these data sets available, and you can get them, and you can read his write-up on it. But for our purposes, we're just going to use the ImageNet data set. We're not going to look at the ImageWoof data set in this lecture. So the first thing he says is that even 13,394 image files, and even the small sizes are too large to keep in memory for most normal, even expensive systems. Like, I think Jeremy has a pretty good rig, and he said that even in his rig he can't keep all those images in memory. So he built this data block. He and Sylvain built this data block API where you can read in one image at a time and train that way. So it's like stochastic gradient descent. So let's see. Yeah, there's another. So I'm just going to give the schematic. What it does is, the whole point of this data block API is to prepare your data, do all the pre-processing necessary before the modeling step. So Jeremy gives the sort of a high-level introduction to what he set out to do with this data block API. And he said you first need to get the files, You need to split off a validation set. And there are many ways to do it, and I think the way that they do it is I think they have many different ways built into the API, but one particular way is like when you have directories, all the files are in directory structures, and so the API knows how to get them, knows what the directory structure looks like, and knows how to get them out. Then for each image, you might need to transform the image. You might need to transform it to a tensor. You need to load the data to get ready to put it on CUDA. And then you might need to do some more transformations on batches that have to do with like normalization or statistics or something like that. And then once you're done with that, you put everything together into an object called a data bunch. And that data bunch has all these methods and properties that allow it to be that the modeling API knows about. And so it's kind of like a smooth interface with the modeling API from Fast.ai. So let's see. So I just took some notes on some of the things that they built, and my screen is hiding it from me. So let me see. Yeah, there's this function called getFiles, which is Jeremy's very proud of this. It's a fast function for reading images. It uses I forget what that thing is called, scan data or something, and he demonstrates that he can read these the image files in incredibly fast. Then he built these classes called list container, item list, and image list that enable the construction of the data set in the right format that you need for modeling. And then he has a grandparent splitter function to build train and valid data sets, a split data class to help that grandparent splitter, processor and category processor classes to do the basic processing on the data, like that would include things like batch norms and so on. Let's see, processed item list, labeled data class, and then he has another thing called transform resize fixed, a resize fixed transform that resizes the images to 128 by 128. So remember, we started out with what is it? I forget what the numbers were. 160 by 213. That was the input size, and he has this transform that resizes the images to 128 by 128. And I think he does this by grabbing. I think, correct me if I'm wrong. He doesn't squish the images in their aspect ratio. He just goes in and grabs and crops it to 128 by 128. Is that right, according to people that are maybe more familiar with this? Anybody have any comment about that? Michael, do you know if he's cropping the image to 128 by 128, or if he's basically squishing the aspect ratio to 128?
Yeah, I think he's changing the aspect ratio from what I saw.
Oh, okay. I see.
Yeah.
Okay.
Yeah.
Okay.
And I think he said it's not the best way to do it, but he said it's just to demonstrate how this works. So I guess it's not the way you want to do it if you work with this on a real project.
Yeah, maybe we're thinking about to see how one could do it differently. I thought somebody talked about a possibility of just going in and cropping, cropping the 128 by 128 out of the center, but then you could miss key features or something. So maybe that's not such a great idea either. Anyway, and then the last thing is this data bunchify, which is kind of a cute name, but it basically is the final step in putting together the data set the way that the modeling API expects it to be. I just wanted to note that on a Windows machine, I've had some trouble getting some of these notebooks to work, and people have helped me on the forum, and they told me that you have to put num_workers equal to 0 if you're working on a Windows machine, which kind of sucks because then you can't exploit your multi-core CPU for fast pre-processing. So I noticed that my times are a lot slower than Jeremy's when I do pre-processing. They may be 3 times as slow as Jeremy's when I do pre-processing, and maybe only 1.5 or 2 times as slow as Jeremy's when I do the training on the GPU.
Yeah, I think that's the PyTorch. That's the PyTorch back with this, I think.
Yeah, so that kind of gives me an incentive to try to install another disk drive on my setup and get a Linux boot disk, and so I just have Linux and use it from there. Unfortunately, my laptop, the fastest, it has space for 2 drives. One is the really fast one, the NVMe drive, and that one I bought it, and they by default they installed the boot disk it's a Windows boot disk. So I can install a second drive, but it's not. It has to be a SATA drive. It's not the fastest kind of drive, and that's the one I have to put the Linux kernel on. So it's good enough, I think.
You can install 2 OSs on the same drive as well. That's possible if you have the space for it.
Well, I have the problem with that is that my first drive is 500 gigs, and so that's not huge. My second drive will be 2 gigs. 2 terabytes. So,
2 terabytes, yeah.
Yeah, so that's the one that I'm going to make a Linux boot drive, and it's not my fastest drive, but I'll just.
I would recommend putting the Linux on the NVMe drive and moving Windows to the SATA drive.
I don't know how to do that, but I should probably look into that.
I'm happy to help with that because the reason behind that is if you put swap on SATA, that'll be slow. So how swap works is once your RAM is full, Linux starts putting stuff on the swap, and you'd want that to be on the faster drive.
Okay.
Maybe you have space for both systems on 500 gig though.
Oh yeah, maybe I can try that first and see how that works.
Yeah.
On my laptop, I have a 500 gig NVMe and a 1 TB hard drive, so I'm dual booting both the OSs on the NVMe drive. That's working fine for me.
Oh, so you have a dual boot system,
yeah,
on the NVMe. Okay, that's what I'll try. If it works for you, I'll try that.
Sure.
Yeah. Okay, so anyway, the bottom line is he runs on his ImageNet, and he gets 72. He uses a 1-cycle scheduling with cosine annealing. There's some plots in the, I should have put them up here, but it shows what the cosine annealing scheduling looks like. And he gets 72.6% accuracy on, doing very little, just running it the first try. And a good score is in the 84% or something. So he said, at least he's on the right track. Let's see. So at the bottom right of this slide, I have the series of commands that you use in this API to get your data and put it in a data bunch, and then it's all ready for modeling. So there's just like 6 lines there, and the last step is the data bunch step. And this is the place where I have to change. You see where it says num_workers equals 4. If you're on a Windows machine, you have to put num_workers equals 0 because it can't handle. Num_workers is parallelizing the task on your CPU. So most CPUs have 4. You have 4 cores or maybe more, and this num_workers equals 4 allows you to parallelize the preprocessing on your on your CPU. If you have a Windows machine, you can't do that. You have to put num_workers equals 0. So it slows you down with the preprocessing step. Yeah, so that's it for this slide. Are there any questions on this? Oh, and the final thing is, there's a paper that he that he refers to this bag of tricks for image classification and convolutional networks. I think that Sanyam reviewed that for us some time ago. Jeremy's one-line summary of that paper is this: it really is 3x3 kernels everywhere. That is his summary of this paper. He says that's the only thing you need to take away from the paper. Just don't use the 5x5 kernels anymore, or the 7x7 kernels. The 3x3 kernels are better. I don't know why, but I'm going to look into that. Yeah.
If you need more context, so the paper mentions this modification inside of ResNets. So as you know, the paper is aimed at improving accuracy while keeping performance and speed in mind. So they realized that if you toggle with the kernel sizes, I assume that was through experimentation over intuition. They realized that 3x3 kernel size was really helpful. So there's a proper section, the fourth section, like towards the end of the paper, where they mentioned what all kernel sizes were useful. If you're interested, that might be helpful.
Just one quick question with regard to the 3x3 kernel. I thought in the last lecture he said we need a first kernel need to be a bigger, like 7x7 or a 5x5 rather than a 3x3. So I got confused there. Like, what's the kernel size, initial kernel size we would require?
I'm not sure. I haven't watched either of the lectures. I'm just giving context about the paper. I'll have to double check.
Yeah, I remember that too. I remember he did say something about that too. And I also remember that in Andrew Ng's class on CNNs, he does do things with different. He does do things by going from a 7x7 to a 5x5 and then to a 3x3, something like that.
That's correct.
I'll check the sizes and let you know. Please ignore my comment for now. I'll double check and post in the channel.
Yeah,
if it's confusing, just ignore that for now.
In the lesson as well, this time around when he was explaining, he did 3x3 and 3 channels. But in the last lecture, he was saying if you use 3x3 kernel, you're not learning much. So you need to have a first kernel, as most of the people are using 7x7, but Jeremy tend to use 5x5. And I say that's a pattern regularization or so on. But I got confused that then we in this lecture we again start coming down to 3x3. So it's just maybe I'll rewatch and then probably see what he meant by it.
Yeah,
I'm sorry, I'm not sure either. I'll check and post in the channel.
Fine.
Yeah, and I think I'll review that paper which Sanyam reviewed for us, but I didn't have a chance to read it myself. The bag of tricks, and see, because apparently there is where they did the research showing that 3x3 is best. So
I'll share the relevant links to the paper in the chat, my overview as well, if you're interested.
Great.
Yeah, Joseph, one request. Would you mind going into a presentation mode so that we can see only one slide? It will be a little bigger.
Oh, I thought I had done that. I thought I had done that. Let me try this.
Just press slide.
Well, see, I have it displayed on a different screen, and so I'm seeing it on 2 screens. One screen it's apparently not in presentation mode, and that's the one you're seeing. And the screen that I'm seeing, it is in presentation mode, and I'm not sure. Let me see if I can fix that.
If you could, otherwise we're fine.
Yeah, let me see. The main screen, let me see. Did that change it?
Yep.
Okay,
that's it.
Super.
Thank you.
I'm sorry. I thought that I kind of asked people at the beginning, did you see the full screen? And I thought somebody said yes. So that.
Yes, it was my mistake.
Yeah, this is better.
Thank you.
Okay, so that's the data block. Let's see. And now. There it is.
One of the question I have, Joseph, did you, like I myself, like I didn't run the notebook, but did you manage to run the notebook and figured it out how he's creating labels for the images?
Well, I'll tell you what, yes and no. I managed to run all the notebooks. My goal before I presented this was to run the notebooks and to understand them all, but that just didn't happen. There wasn't enough time. So I'm going to be working on that over this next week, trying to understand what goes on in the notebooks. I did I was able to run the notebooks to completion and get a good broad overview of what they do, but the details, there's a lot of details, and
Yeah,
I
yeah.
don't understand the details.
Yeah, through the videos, I could like, you know, he's doing a parents and a grandparents for splitting into a training and validation. That makes sense. But interestingly, when you pick an image, how would you label it? So I didn't get that part through a video, but you're right. I think it's more of an experiment thing.
Okay, so he has the training data, and he gets the labels out of the directories. Like there are various methods for getting the labels that are all encompassed in this data bunch. And I think that the version of data bunch that we're writing ourselves is outside of, what does he call it? We're reconstructing Fast.ai, right? So we've constructed a sort of a mini version of the data bunch that's for image data in a certain way. I think he has methods to get labels from either file names or label files, and I think in this case the labels might be coming from the file names themselves, but I shouldn't say that. I should look into it carefully. But he does have methods built in to how to get the labels. The training data and the validation data are labeled already, and it's just a matter of getting those labels. And sometimes the labels are buried in the file names. You know, there's some string that gets the file name.
Yeah, that's correct. And again, because he's trying to create, I think, 10 classes, and if he picks the random images, I'm not sure whether all the images are classified into 10,000 directories or they're sitting together. If they are in a 10,000 directories, then it makes sense that he can pick up a label automatically. But if all the images are sitting together and we are randomly picking just 10% of it, then how would you label it? What's that program who's gonna label?
I think there's the assumption is that somebody has done something smart in the way they provide the data. And one of the smart things to do is to label the directory, is to have is to divide the images into folders according to their label. So like if you have 10 classes, then you label folder 1, folder 2, folder 3. Folder 1 has all the images with class 1. Folder 2 has all the images with class 2. Folder 2 has all the images with class 10. That would be a smart way to do it, right? And then it would be very clear how to get the labels. And I think that's what he's assuming in this simple F5 version. Does that make sense?
Yeah, it does. Yeah, thanks.
But again, I'm talking off the top of my head, and the best way to do it is for me to go in there and look at the.
You're right. I think it's more of like I need to run the notebook to see how exactly it's working. So yep.
Right. That's what we all.
All right, thanks. Yeah.
So then we move to notebook number 9, which is again another one of these crown jewels. They're building this generalized optimizer. And it looks like it's sort of in flux. They're building it as we speak. I mean, it's really cool to see it coming together. And I wish that I could be a little bit farther along so I could help out a little bit, you know, being one of the people that contributes, but I'm not that far along yet. But anyway, so there's 2 paper references here that he talks about. This one was L2 regularization versus batch and weight normalization. And Jeremy likes to make big sweeping statements, and he says this first paper makes this revolutionary statement that L2 regularization does not have a regularizing effect. And then he goes on to say things like, we don't know what the hell we're doing, and nobody knows what they're doing, and blah blah blah. But the thing to bear in mind is that the paper didn't say that L2 regularization doesn't have a regularizing effect. It said L2 regularization doesn't have a regularizing effect when it's used in conjunction with normalization. And that's because the normalization is kind of undoing, in some way it's undoing the regularizing effect. So the point that Jeremy makes is that L2 regularization is doing something, but you know, when you're using it with batch normalization, it's doing something, but people haven't really understood exactly what it's doing. And I think there are a number of papers out where they study this and try to tell us what they think it's doing. And one of the papers is this second paper here, 3 mechanisms of weight decay regularization, by this team, Roger Gross, I think he's at MIT, I'm not sure. Anyway, he seems to have found he's done a bunch of studies with the students, and they find some answers to what exactly is weight decay regularization doing. All right, so again, he builds this class called Optimizer, and then he has this another object called param groups. And param groups used to be called layer groups. I think back in course 1, you remember when he divided the layers into the later layers and the earlier layers, and when he did the he used pre-trained network, and he froze all the layers, and then he unfroze the later layers, the last 2 layers, and then he unfroze the progressively, and then he unfroze all the rest of the layers. So he divided the layers into basically 2 groups, and he called them layer groups. So now he says that a better name for that is param groups, and he doesn't want to use layer groups anymore. So we have to all change our vocabulary a bit. The structure of a layer group is a list of lists, and I've got it written down here. It's basically a list that has 2 lists in it. And the first list is the hyperparameters for all but the last 2 layers. That is the deeper layers. And then the second element in the list is the hyperparameters for the last 2 layers. And in what form are these hyperparameters stored? They're stored in a dictionary. So this basically is a list of it's a list of lists, and each of the 2 lists inside of it has a dictionary in it, which holds the key and the values for the hyperparameters. Does that make sense? So there would be, so for example, you could have a dictionary that has one entry would be learning rate, and that would be the key, and the value would be 10 to the minus 3. And then another entry in the dictionary might be batch size, and then the key would be batch size, and the value would be 64, something like that. Does that make sense? So the hyperparameters are stored in a dictionary, in dictionaries. Then he talks about some of the components that he built. He built a thing called a stepper with a function called sgd_step, and it basically is a simple function that performs a single stochastic gradient descent step. And then he built another class called param scheduler, and this is where you get those learning rate schedules like cosine annealing, and I forget what some of the other schedules that they've come up with, where one of them is like a sharp linear ascent and then a sharp linear descent. I don't know what he calls that, that way. But in this one, these notebooks, I think he's using cosine annealing. Then he talks again about weight decay and L2 regularization, the difference between them. I didn't make a slide on this, but maybe I should have. Remember again that L2 regularization is when you add a term to the loss function that consists of the sum of all the squares of all the weights. You remember that? And there's a multiplier in front of that term. So for example, for a simple loss function, a simple mean squared error loss function, you would have the loss function being the sum of the squared errors, the sum of the mean squared errors. That would be the first term of the loss function, and then the second term would be some multiplier called beta or something times the sum of all the squares of all the weights. Does that ring a bell? That's L2 regularization, and what it does is it drives it tends to drive the weights closer to 0, so it constrains them, and in that way it regularizes. It prevents your model from going crazy and being fully flexible to do whatever it wants. It forces the weights to be relatively small, and therefore the model is constrained and is not as flexible as it could be, and that gives you the regularizing effect. Okay. Now the other method of doing this, doing a similar thing, is called weight decay, And here, you leave the loss function alone. It's just the sum of the squares of the sum of the squares of the errors. But now you add the extra term into the correction. So remember, the weight would be equal to alpha times the gradient, or negative alpha times the gradient. That would be the normal scheme for weight decay for stochastic gradient descent. Does that ring a bell? The correction, the update of the weight is the old weight minus a constant times the gradient. That's the back propagation, right? So weight decay is when you add an extra term to that correction, to that update, and that extra term is the derivative of the sum of the squares of the weights. Does that make sense? So it's like you're doing the same thing, but in one case you're accomplishing it by changing the loss function, and in the second case, in weight decay, you're accomplishing that by directly changing the updates to the weights to be the same as they would be if you did L2 regularization. So hopefully that's clear. I suspect it's not. If it's not, go back in the lecture. I think he has some nice. There are some nice screens in the lecture video where he does this, and it's also been discussed in the past as well in the first class. Okay, so in this generalized optimizer, then he adds adds a scheme for momentum, and then he has this class called stateful optimizer that keeps track of the state, and you need to do that when you're doing momentum because it's related to exponentially weighted average, and so you need to know this in order to calculate the exponentially weighted average. You need to know all the past states, or at least the last state. And then he has another class stat that keeps the statistics like the means and the variances of the weights and so on. And then because of momentum, you need one of the terms involved in momentum is averaging the gradient, is an exponentially weighted average of the gradient. So he has a class to calculate that, and then having built all those things, he then does the momentum step itself. And with this function momentum step. Unfortunately, I don't have time to go into the details of all these functions, and to be honest, I didn't go into the details of all these functions myself yet, so so I don't want to say that I know what all this stuff's doing. This is kind of a high-level review. Any questions down to here? Okay, can I move to the next? So we're still talking about the optimizer. He quotes another paper, which is kind of exciting. It's called Reducing BERT Pre-Training Time from 3 days to 76 minutes. And BERT is this new language model that I forget who developed. I think it's Google.
Yes.
Everybody's really excited about it, about BERT. But this paper is even more exciting because they introduce another method of optimizing. And it's called LAM, and it's basically the equations are in this paper. And so Jeremy goes through these equations. But before we do that, let's go back and talk about momentum. He goes through about how you debias the momentum and the squared momentum in the formula. And then he talks about atom, because atom is an improvement on momentum. And in words, atom is dampened debiased momentum divided by dampened debiased squared momentum. And dampened refers to the exponentially weighted moving averages that are involved in computing the momentum. And debiasing means dividing by. See, I really need a whiteboard here to talk about the momentum formula. But what you're doing is you're adding like 0.9 times the previous weight. You're updating the weight by 0.9 times the previous weight plus 0.1 times the updated weight. I think that's how it goes. It's not the other way around. And the 0.9 is, I guess they call it beta, and so beta can be. They say that beta, a good value of beta is 0.9, but in general, it's beta times the old weight plus 1 minus beta times the updated weight. And in that way, if you keep doing that time after time, you're basically dragging the weight. You're not letting it change as much as it wants to change. You're saying keep some memory of what it used to be, of the weight in the previous step. Don't just change it. So it's being very conservative about changing weights. And when you repeatedly do that, you build up this factor of 1 minus beta to the n, where n is the number of layers or something like that. And when he talks about debiasing, it means dividing out that factor of 1 minus beta to the n. And Jeremy mentions that Sylvan has, I should have put a link to it here, but I didn't yet. Sylvan has written a beautiful LaTeX document showing the mathematics of what happens when you're doing exponentially weighted averaging. It's really actually beautiful, and showing why you need to divide by that factor of 1 minus beta to the n. And so again, that's the debiasing step. You need to debias the numerator, and you need to debias the denominator. And then Jeremy mentioned that, well, after you debias the numerator and denominator, you canceled out the debiasing factor, so you didn't really need to debias. But I think in the work that he does from now on, I mean, this was introduced last time, and in that notebook from last time, Stas Beckman pointed out that the debiasing steps cancel each other out, and so you really didn't need to do it, and so you save yourself a little time in those notebooks from lesson 10. But Jeremy points out that we do need to do the for this LAM method, we will need to keep the debiasing steps. And then there was a little bit of a kerfuffle during the lecture about where the epsilon goes. Let me see if I can. In all of these formulas, okay, so I don't have the formula for atom here, but this is so LAM is sort of a new upgraded version. It's similar to atom, but more sophisticated and better. In both of these, in both atom and LAM, you have this formula that has somehow some kind of an average of the gradient that's debiased, and then the average of the squared gradient that's debiased. And then you take the square root of it. So you're averaging the squared gradient. That is, you're taking gradient squared and summing up all the gradients squared. And then you take the square root of that. That's what this step is. And then you have to add this factor, this term called EPS that helps stabilize things. As you might imagine, if the denominator here got very, very small, things could become unstable. So they stuff in this fudge constant called EPS, epsilon, to prevent things from getting out of control. So I forget the value that he, well, here's what he says. In LAM, it should be 1 times 10 to the minus 6. That's what the EPS is. But anyway, there was a big kerfuffle during the lecture about the fact that Jeremy thought that the EPS should go inside the square root. In other words, you add up all the squares of the gradients, debias them, and then add epsilon. So the epsilon would be added right here. Oops, damn it. Let's see, go back. Yeah, so Jeremy was thinking that the epsilon should be added here before you take the square root. And Rachel stepped in and Sylvan stepped in and said, no, the right way to do it is, according to the papers, the gradient, the epsilon is added outside the square root. And again, to understand that and appreciate it, I don't have a clue. I'd have to read those papers, which I intend to do, the papers about Atom and Lamb. Okay, so here's what's going on in Lamb then. The step is the average gradient debiased divided by the square root of the average square gradient debiased with this little epsilon step, and then you add a weight decay times p dot data. I'm not sure what p dot data is. That might be the I don't have a clue what p is. But anyway, WD is this weight decay. This is weight decay constant. That is it's a hyperparameter.
P is the first parameter of a Lamb step function.
Okay, it's the first parameter of the Lamb step function. So it's given, it's passed into the Lamb. Yeah, there it is. It's passed in. Okay, and data. Okay, so data would be how you get that. P must be some kind of data structure, and data is probably some property of it that you need. It's a hyperparameter. So okay. So that's the formula, and then Jeremy talks about how you can, you shouldn't be cowed by a lot of this complicated math, because sometimes you can find patterns in it that help you to sort of at least get a better idea of what it is. In this case, he says there's a couple of patterns to look at. The momentum has this is a linear combination of the momentum at the previous step, some constant times the momentum at the previous step. That's mt minus 1 of this layer, plus 1 minus that constant times the momentum times the gradient at this step. So instead of just adjusting by the gradient, by some constant times the gradient, you're constructing this quantity called momentum, which is a linear combination of the previous value of momentum adjusted by the gradient. And again, this is meant to be a conservative way to let the weights change, keeping some memory of what they were previously, not letting them have such freedom to change. Back. Yeah. And then so you look at this M, and then you look at this V, and V, the formula for V looks very similar. And then I think what you need to know is that V is the squared gradients. So so there's a momentum, and then there's a squared momentum. And so V is the squared momentum, I'm sorry. And so the squared momentum is also a linear combination of its previous value plus 1 minus that constant times the next times the gradient squared itself. And so there's a pattern there in M and V that Jeremy points out. And then there's a pattern here when you do the debiasing. So here's the denominator is what I was telling you about, the debiasing factor, 1 minus beta to the time, t, where t is the time step. And so you have to debias the momentum, and you have to debias the squared gradient as well in the same way. All right, and then I'm not sure what R is. Oh, R is the norm of the weights. Okay, R is the norm of the weights on the previous step. S. There's that formula with the epsilon in it. So V is again the squared gradients, and then this is consistent with what Jeremy said. So you take the square root of. Now this is weird because this is not consistent with this. This says you take the square root and then add the epsilon. Oops, sorry.
Yeah. Actually, it is.
Pardon?
At large step, you've multiplied the weights with the p data, right? So that is what it's been added. And the epsilon is below. It's added as the square root. Is it not?
The epsilon is inside the square root there. and outside the square root there. So I'm a little confused.
And isn't that what he was doing during the lesson as well? He was putting the epsilon inside the square root?
Yes, yes, he was putting the epsilon inside the square root. Maybe, maybe, I don't understand. What I do see is that these two formulas, this formula here in code, is not consistent with the formula written out here. So need to think about that some more and resolve that.
But if you push the epsilon inside the square root, would that make the formula then it will be consistent, isn't it?
Yeah, if I take the epsilon and put it there, then it would be consistent. But that's what they were saying is that's what Susan and Rachel were saying isn't right.
Correct. Yeah. So it looks like ultimately he was right.
No, I think they were right, but maybe it's a difference between atom, the formula for atom, which I didn't show, but it also has an epsilon in it. And maybe in the atom formula, the epsilon has to be outside the square root, and in the lamb formula, it has to be inside the square root. Because obviously, this must be the correct form for lamb because it's from the paper, it's directly from the paper.
Right.
The implementation, and the implementation here looks like it's wrong. So it could be that they were discussing atom, the formula for atom, and in atom, the epsilon has to be outside the square root.
Yeah, in the upper screenshot you've shown for atom step, the epsilon is outside the square root. The same slide.
Oh, it's the same slide. Okay, let me.
Yeah.
Yes, I do have atom. Okay, sorry, I thought I didn't have atom on. Yeah, here the epsilon is outside the square root, and I think they made a mistake here because this is supposed to be the implementation of lamb, and lamb we see that the square root has to be inside.
Okay, so for atom the epsilon stays out, and for the lamb it goes in.
That's what I think. That's what I think we get from a lecture like this. Okay, so what time? How are we doing for time? We are at almost 10. So let me move on to the next slide. I didn't write too much about this. He basically had this class called Learner that we learned about last time, and they were all excited about it in lesson 10. And then Jeremy found a clever way to refactor it, and he now calls it Runner. And again, the details, you have to look at the code. I didn't look at the details, but he did it in some very clever way that gains speed. And now there's no longer anything called Learner. There's no longer anything called Runner. That was the thing he introduced in lecture 10, which he was so excited about. Lecture 9 or 10, I can't remember. And now he's refactored it and he calls it Learner. And so he has this notebook 9B Learner where he shows that. Okay. I can't. Yeah, there we go. Okay, and then I think the last or second to the last notebook is this clever thing that Sylvan came up with, adding progress bars to the learner. And so we have a notebook that goes through it, and we call it 09C_add progress bar. It's a progress bar. And I took a screenshot of it to show you how nice it is. As you're training, you see the progress bar, and you're not left in the dark wondering how long you're going to have to sit there in front of your machine until it completes. It's really a nice feature. I wasn't able to get this notebook running, and then I wrote a note on the forum, and somebody came back, and Jeremy came back and said, look at the very first line in the wiki for lesson 11. It says you have to update the callback function. You have to update this progress bar function. And I haven't tried it yet, but presumably if I update it, and they even show you how to do it, it's just a conda update kind of line. And once you've updated it, it should run. I just had a problem with it on my Windows machine. It needed to be updated. I'm sure that once I do that, it'll be fine. So, so this is what it looks like. I can't make much sense out of it yet, but I will. Anyway, and the last notebook is data augmentation, which it turns out to have a lot in it. So Jeremy says that augmented data is really, really important, and I haven't done very many. I haven't gotten involved in Kaggle competitions, but I mean to. And everybody who wins Kaggle competitions is they're using augmented data to help them along to win. What augmented data does is it basically helps you to extend your training set to be much bigger than you really have. You don't have much data, but if you augment the data by doing various transformations on it, then you have effectively a much larger training set. And we all know that large training sets lead to a better more trainable model and better accuracy. So he uses, for this particular notebook, he uses what's a thing called the Python image library called Pillow. It's also called PIL, and it just has a lot of functions that manipulate images in it. But the main point that I get out of this is Jeremy says that once you've done the augmented data, don't just move on. Understand that data, look at it carefully. And again, augmented data can be more than just images. You can have audio data. As we're going to learn about audio data in the next few lectures, and you can make augmented audio data from data that you already have. There's let me try to think of other time series data. You might be able to augment that data as well. Anyway, the point that Jeremy makes is look at that data carefully. Don't just presume that it's all good. And the example that he gives is on this tench fish thing, where he does different kinds of transformations on the image, and finds that I wonder if I wrote this anywhere else. Remember the man with the shirt, and he did various different kinds of augmentations on those images. The man with the shirt holding the fish, and some of them lost the detail on the shirt. And so by looking at those images and looking at trying various different kinds of image augmentation, he was able to see that some forms of augmentation leave the checkered shirt invariant, leave that in place, whereas others blur it, and so you're losing information. So that helps him to pick which kind of augmentation he wants to do. Let's see. He makes the point that calculating with bytes, that is, I guess in an image, an integer is 64 bits, and float is 32 bits, and a byte is 16 bits. And he says that calculating with bytes is really, really fast, and so you should do as much of that as you can in that form. Do a lot of the image augmentation in bytes, because that makes it much faster. And image augmentation is apparently the limiting step, one of the limiting steps in these models. I think he talked about what was that? The Fast.ai benchmark thing that he did, that they did a couple months ago, where they got like first place on this benchmark test. They carefully did their augmentation in bytes in order to gain a lot of time. That's how they got their scores so low. So do transformation on bytes as much as you can. You're limited in some cases. If you do too much in bytes, you might get round off errors and so on. So you have to watch that. Do as much of your manipulations as you can on bytes, then convert to the tensor. Then he points out, he talks about various kinds of augmentation, like resizing the image, randomly flipping it, randomly cropping it, and then resizing it, transposing it. These are all various ways to alter the images and make them kind of like, you take an image and you kind of do this to it, and now you have a new image for your training set. Or maybe even you can do 10 of these operations and you can get 10 new images for each one. But he says that the most important augmentation in ImageNet is random resize crop. So I guess that means you take the image, you resize it, but I'm not sure you resize it to some random number. I think the randomness comes in with the crop. You crop it to some random number, like, and he says that they usually pick between 8% to 100% of the pixels, and so he points out that you often lose, not often, but you can lose, and a lot of times you can lose the part of the image that would be associated with the label. Like, for example, in the fish, you know, the tench fishing images that he has, if you pick the wrong part of the image, you won't have a fish in it anymore. And so, and yet the image in your training data set, the image will still be fish. And so so in that sense, your labels become noisy when you do this random resize crop. But he says that this is not a bad thing. It leads to some regularization. The noise adds some regularization, prevents your models from being too flexible. And then finally, he talks about affine transformations and rotations and interpolation. So rotations are easy to understand. You just take the image and rotate it, you know, 45 degrees or 30 degrees or 90 degrees. That's a major form of reprocessing of augmenting images. And he shows how rotations can be done with a matrix multiplication, which is kind of cool. Then he talks about this perspective warping, which is something that they've developed. And this allows you to take an image and transform it so that it's seen from a different angle. So if you're looking, so for example, if you're looking at a cat face on, you do some kind of a transformation where you have this cat image as if you were looking at it from 25 degrees off of face on. So they've built this perspective warping piece in their image augmentation API. So again, this thing is becoming another crown jewel of the Fast.ai, of the whole Fast.ai. This data augmentation section. I think that they're ahead of a lot of other machine learning libraries. What I'm worried about is that, you know, like Jeremy and Sylvan are two people, and they've got Stas, Beckman, and they've got a handful of other people working on this with them, and they're doing all this, and they're coming up with these state-of-the-art results and so on. And what I'm wondering is how long this can go on, because you can imagine that people from Facebook and Google and Apple are looking at them and saying, hey, you know, we can do better than that. We've got like armies of people. We've got armies of data scientists, and, you know, the best data scientists in the world, and we can get together and make even better stuff than they've made. So I'm wondering how long Fast.ai is going to stay on top. I hope it's going to stay on top for a long time, because we're spending a lot of time learning it. So
maybe these big tech companies just simply buy them. Yeah,
maybe. But you can imagine, I mean, this is the work of a handful of people, and you know, these big companies, they have hundreds of data scientists, or highly qualified data scientists, maybe even thousands of them. I think
Joseph, Joseph, Jeremy is preparing army of the data scientists via his online code.
That's true. That's us, right?
I think he keep on saying to the online audience as well as the audience which is present that you will be going experimenting, and then you will be beat me. So that's the subtle hint that come and join, and then or contributing to the open source. So
yeah.
I guess definitely.
Yeah, and you're absolutely right. I mean, and also like San Francisco State is a major player now in Silicon Valley. If you look at on LinkedIn, if you just browse around and look around, you'll find like there's literally hundreds of students who are students in this San Francisco State data science program that are also interning in Silicon Valley companies and transitioning to full-time roles in these companies. So it is really an army of Fast.ai people that's entering the market now.
Correct. Yeah.
Although there's also the things like AutoML from Google, as there was on Twitter and stuff that this AutoML, which is the automatically generated model that beat almost all people, took second place in this Kaggle competition. So that's something that's really and there was two more. So the Generalized AI from H2O, it took like 5th and 8th place. So in a top 10, there were 3 automatically generated analysis. So that's
is AutoML connected with Fast.ai? I seem to remember that.
I'm not sure. That's Google, so I'm not so sure.
Oh, it's Google. Okay.
Yeah.
AutoML. Yeah. Well, I guess we all want to go learn AutoML now.
Yeah.
But I can't imagine that people who are using AutoML know nothing about machine learning. I'm sure they have to know something. I mean, maybe eventually, you won't need to know anything about machine learning, and you just. I don't see that though. I think you really have to.
Joseph, could you mute everybody, please?
I can. Yes.
Yeah.
No. Manage participants. Mute all. Okay, and then. Okay, can everybody still hear me?
Yep.
Yeah.
Okay.
We can hear you.
Okay,
Yeah.
we're good. Okay, I'm basically done now. I think. Let's see. I just have one. I noticed this thing early in the morning. This fellow, I forget what his name was. He put up a very nice addition to the things Jeremy says to do section in the forum. And here's the link to it. There's some interesting things that he. Let's see if I go there. Can't go there. No, maybe I can. Oh, can't get it. Anyway, it's worth checking out. He's basically taken a lot of things from Jeremy's video that I missed, that I didn't focus on, and he pulled a lot of interesting points out of that video and goes over them here. So it's worth checking out. So that's what I have. Is there anyone?
Could you post that link into the chat window, or perhaps share the slides?
I will share my PowerPoint. Is that? I'll convert it to a PDF so that, and then I'll share it into the website, into our Slack.
Yep. Thank you.
Okay. So does anybody have a mini presentation or anything that they wanted to talk about?
This is Mehul Sampath. I took part in that Kaggle competition, the Kaggle Days. And so my team, I teamed up with Sairam, who's also part of the study group. And we came 10th in this competition.
Wow.
Yeah. If you want, I can talk about it for a few minutes.
Yes, please.
Yeah, that would be interesting, definitely.
Okay, and so what happened is both of us are new to tabular data. We mostly do imaging data. So we just decided to focus on a very simple approach. Wait, let me see if I can share my screen and show you the kernel we used. Wait, let me see.
Can you link to it on the chat later on?
Yeah, sure. I'm going to make it a public. It's basically, we just used a Kaggle kernel, and we used a model. So it's not, and we used a non-deep learning approach.
So maybe, sorry to interrupt. So maybe Joseph, you stop sharing, and then Mehul, then you can start sharing.
Okay.
Afterwards.
Sharing
now,
is
all yours. Yeah. Mehul, you can share now.
I don't see it yet. Wait.
Yeah, so I should start sharing my screen.
Yes, please. Yeah, we can see your screen.
Okay, so this competition was it's basically tabular data. It's from manufacturing from a manufacturing company. It's like you have to detect if there is a defect in the manufacturing batch or not. So the target variable is basically 0 or 1. Okay, and there were a bunch of features like categorical and categorical and continuous features, and they, to start off with, they gave us a kernel to work in. Oops, where did yeah, that's the one. And I have used so basically you have gradient boosted decision trees, and there's another very popular package called light GBM. Um,
It's from Microsoft, I think.
yeah, right. It's a Microsoft pack. It's basically the reason I like it is I can try multiple approaches with just one package, and so for example, I can try gradient boosted decision trees, I can try random forest, and then a couple of other things with just one package. Okay, so since both of us are new to this, we used a very simple approach. We used a single light GBM model. Um, and then I'll show you later one of the teams that came eighth. That was the team from H2O.ai. Um, they did automated modeling, and they used around 40 models, and we will see the differences in the results. Okay. So in this basic case, we started with a kernel that was shared, and yeah, so the initial, yeah, just basically loading and testing loading the train and test data. It's not too big. It's about 400,000 rows. I learned some new things about sklearn. Oh, and one other thing, we just decided to use a non-neural network approach. There were some other teams that that did like an ensembling of gradient boosted model and with a neural network. But I think that a lot of people overfitted, and so initially, when you're looking at the public leaderboard that was just showing the results with uh, um, with 50% of the test data. Me and Sairam, we were pretty low in the leaderboard, but when they released the full data, we moved quite a bit up, and I think it's because we didn't overfit. Okay, so what did we do? Um, so the initial LGBM classifier is they had something, and they didn't have any of these parameters. Okay, so and I will tell you why we picked each of these parameters. I had experience from a previous Kaggle competition where I was using light GBM, and I have a link where so one of my problems is that there are just too many parameters, right, to tune here. See if just a second. I just want to quickly. No, I don't show that. Okay, this one. Yeah. So this. This I had found in the previous Kaggle competition. It's basically, see, you have all these parameters for both, if you whether you use XGBoost, which is the other popular package, or Light GBM. But I want to get an intuitive understanding of, okay, what parameter I should change and what I should play with. Um, so for example, here it gives you some information about, okay, the default value is 0.1, and um, some details about how you should change this parameter. Okay, so um, maybe you start with a lower value and then fix it after some iterations. There was another key one for me is regularization. So basically, let's say how to put this. Say I have 200 features, right? So if I put my regularization as infinity, right, I'm just penalizing everybody, and it's like, okay, none of the features are useful, and basically everything, nothing is going to be selected. So the default there's no regularization. The default is 0. So one of the things we decided to play with is this regularization factor, and we were basically trying different values for this regularization factor. So let me go back to the kernel. Sorry, I'm jumping around a little bit. Okay, that's it.
Yeah, so we see only on your screen, we see only a kernel, Mehul. If you're trying to switch between the two, we didn't see the screens. We saw just the
Oh,
kernel.
just the kernel. Okay.
Yeah.
Sorry about that. Do you see something else now or not really?
Yeah.
Okay. Okay. So sorry about that. I just new to sharing.
No, it's all right.
Yeah. So this is the. Let me put this in the chat. So I really like this summary by this person. So what they did is they give you all the parameters and then tell you, okay, what is it related to? Is it related to architecture? Is it related to regularization? So for example, when I pick regularization, I get all the different parameters that will affect regularization. So, and I have some experience with like regularization from other Kaggle channels, and I find it really helps to avoid overfitting. And of course, one challenge is it's we don't know the magic value for the regularization, right? How much regularization to put. Um, so here they say, like, I mean, the default is if you don't, yeah, just don't change it if you're not sure about it. But in our kernel, we basically played with L1 regularization, um, and so implementation wise, it's pretty straightforward. You just say lambda L1 is how much regularization you want to put, the number of decision trees you want in the light in the model, uh, and the learning rate. So one other new parameter we learned while going through this competition is how do I show all of them? Okay. Where was the? Do you see this page about Microsoft Light GPM?
Yeah.
So Microsoft Light GBM had some notes about what parameters to change if you want higher accuracy, what parameters to change um, if you want to avoid overfitting, and speed. So then that's how we came up with, and we had 8 hours. So um, we just played with these 4 parameters, and we were just trying various combinations. We did about, I would say, about 25 experiments with different parameters, um, and in the end we were um, so in the public leaderboard we were 28 at the end of 8 hours, but when they released the full data set, we moved up 18 spots to number 10. Um, and one other thing we did is we are using cross validation, um, and uh, we just played a little bit with uh, threefold and fivefold cross validation, and yes, oh yeah, this was critical. So we ran 30 models, right? The question was which to pick. So we looked at our cross validation accuracy in the kernel, and we looked at what we were getting in the leaderboard. So the one of the hints that was given to us, this I've learned from previous Kaggle competitions, you want your local cross-validation score to be similar to what you see on the public leaderboard. So we had other models which gave us like a higher cross-validation score, like 0.6, almost 0.65, but it was locally here it was 0.65, but on the leaderboard it was 0.61, and that discrepancy is just too big. So then, even though our local cross-validation score was high, we didn't pick that model. We just picked the model that had the closest match between the local cross-validation score and the public cross-validation score.
What about when there's this big delta between private and public leaderboard, which means
Right.
if you fine tune your validation to the public leaderboard, and then the private is completely different. So how to make sense out of that? I just a
Yeah,
little
no,
bit tricky to.
no, that's a really good question. So what we did is I don't want to. Yeah, I try to maximize my performance on the public, right? But if say we never got a very high public data score. We were always like 25 to 30. Um, I think throughout the 8 hours or whatever, or maybe we're just moving up slowly. But we never got above 25. Um, it was mostly just looking at um, the local cross-validation score, right? So it's my local cross-validation score on. Okay, one thing I should clarify. This is the local cross-validation score on the training data, right? So this is I split the training data 5-fold, and this is the cross-validation area under the curve. And on the leaderboard is the score on the test data. Right? So the general concept is uh, does the score on the test and the training are they similar, right? Because is it if you are overfitting your training data, you get a very high local cross validation. Okay, does that help?
Yeah.
Yeah. Okay.
Thank you.
And I had one. So the person who did. Okay, let me pick one more. Okay, so we did so we were. Um, I think our AUC is 0.621, and the Google Auto ML was 0.625, and the the H2 .ai AUC was 0.64, say 0.624. Yeah. So we were all the AUC was differing in the third digit, and one thing I'm trying to run more experiments to see, like, did we just get lucky with these parameters? Because we were, so for example, we use lambda L1 as one of the values we use was 25, and we're like, okay, we don't know. We wanted like a more systematic approach to choose parameters, and there are some sklearn packages for like a grid search. So we found there were two types of sklearn packages, and we found this while doing the competition. There is a more structured grid search and a randomized grid search, and these are both part of sklearn, but we didn't have time to get it running. But that's the next experiment we plan to do is, or at least I plan to do, is just do a randomized grid search and see if I can get a better result than what we had. And one last thing, okay, we're almost out of time. I will show you one of the results from the person who did the driverless auto. Let me copy this. Okay, and this will also show you the top 10 teams. Do you see the leaderboard, like a Twitter page with the leaderboard?
Yeah.
Yes, you
Okay.
can see it. Yeah.
Okay, cool. So we were here, and we jumped up 18 spots. 0.61237. This was the H2O Auto ML. Okay, here's one other interesting thing. So she said she ran it for 100 minutes. We ran our model for like 4 minutes, 4 or 5 minutes, because basically we don't have computation power. We are just using a Kaggle kernel, which is a single GPU. We're just using a Kaggle kernel, and we only use the CPU. And this was the Google AutoML, which was 0.61598. Right, so everybody is doing cross validation. That was expected, but she was using like 43 models, and so maybe you need. So I don't know how much. I don't know if someone has like a good statistics background. Like these are all AUC values, and when you are in the difference in the third digit, is it like statistically significant AUC or not? Um, yeah. Okay. Yeah. That's all I have.
I
Thank
have a
you. That was
question.
very interesting.
Yep.
Yeah.
Yep. Go ahead.
Just curious about AutoML. Like, how does it work? Like, you just feed in your data and then just sit back and then see what it's going to give you the final model?
Yeah, unfortunately, I think yeah they were they released AutoML tables and AutoML vision, um, and they had a.
So I didn't see how AutoML works. I did see how the H2O AI works, the driverless AI. You basically specify the how long you want to spend on waiting for your results, because it can take days, because it will just analyze like all models, and then you specify how how complex the model you want to get, because you can get like linear regression, very easy to understand, or you may get like neural network, and then you specify time, complexity, and I think accuracy you want to get, and then you click start and you just wait, and then it's going to analyze like every model it knows. It's going to analyze all the parameters it can, which can take a long time. So and you just wait, and you get the
Yeah.
result.
So in a sense, like, the grid search do something similar. Like, it's
Yeah,
sort of
so
like. Hmm.
I think on the back end, because I don't know, of course, what's going in the back end, but I think something like that. It just
Hmm.
takes a model at a time. Only if you have more GPUs, it can do this in parallel. I think that's the way they do it. If you have just one GPU, it's going to take like days, if not weeks. But if you have like multiple GPUs, powerful, you can do this AutoML stuff, and it gives you like results quite quickly. But it's going to generate model after model after model, and it's going to try different parameters, hyperparameters, and stuff like that.
Yeah, so the difference between
yeah.
AutoML and grid search is that AutoML, as Michael said, comes up with models. It actually comes up with different model architectures that it knows are good, and it tries them all out. And so that's just scary good. I mean, it's gonna optimize and find the optimal architecture in some way. Just amazing. I just think that it takes a lot of compute power to do something like that.
And one thing I noticed with driverless AI.
I have a question for Mehu. There was this parameter called a number of trees was set, I think, to 100. Did you optimize that somehow? Or is this some kind of default, or?
Yeah, it was the default, but we tried playing with it, like make it 500 trees, and but this one just worked well, and we were worried about overfitting. So now it's I think it's a lot of experience, like to see okay, what we had, like I had some parameters in mind, number of trees, lambda L1, and just play with some of them to try and see what to optimize. But yeah, there should be a more like scientific way to do that grid search. Yeah. And
yes. I have two comments to that. One is I wanted to ask, do you attribute your success in this competition to your? You seem to have a very careful attitude towards overfitting. It seems like you've been very cautious about that. Do you think that's one of the reasons why you succeeded?
I think so. Yeah, because we were so far behind on the public leaderboard. So you can see here, and even this team, like the team that actually won it, is these two guys. We all had lunch together, and they were 31st. and they moved up 30 spots. And they had a similar approach. Like they used one model with just light GBM, and the second thing they did ensembling, but they didn't do anything crazy like 43 models or something. They just did 2 or 3 models, and they said they spent a lot of time on looking at the data, and there were some outliers, so they did some basic stuff to handle outliers, which we didn't do. Yeah, but I think the help focusing on not overfitting, because especially we only have 400,000 training data, and like for example, I remember this team which was number 14. Initially, they had a pretty high score on the public leaderboard, and then they dropped quite a bit on the private.
I see. And the second thing the second comment is to your you said you wanted to come back and try something better than grid, or try grid search, because you didn't do grid search. You did it in a more haphazard way.
Yeah.
There's this thing called TPOT, T-P-O-T, and it's a package that you can use with it's Python. You can use it with scikit-learn.
Scikit-learn.
And yeah, and it's not in scikit-learn, but it's a package that you can install. And what it does is it does a better job than just brute force grid search. It does a principled grid search using genetic programming, so that it won't search values of hyperparameters, combinations of values that aren't likely to be productive. It sort of narrows down the search to the best values. And so that looks like a promising approach.
Yeah.
I put a link to it in the chat.
Okay, thank you very much. I'll try it out and let you know in the next meeting how it goes. Yeah.
Great.
Yeah, one thing about driverless AI is that it's not just with the models, but it also creates so many features which we wouldn't even be able to imagine. So it's like multiply multiple columns, or get averages of too many columns, or like create some sort of additional attributes which we typically people are restricted to create only some. Remember in Germany's random forest example, where the machine learning, machine learning for coders. The first lesson he said that create as many columns as possible. So essentially, driverless AI in H2 at least does that as well to enhance the performance on tabular data.
So did you try the machine learning techniques? I mean, sorry, the tabular data techniques that he introduced in the machine learning class, where you actually use neural networks to handle the tabular data. Did you try that?
No. Oh, it was for himself.
I see. Is it because it didn't work, or is it wasn't promising, or?
It was for you, Mehul, I suppose.
Sorry. No, we didn't. We didn't try all of Jeremy's techniques. We haven't finished all the lectures.
I see.
That was the issue. And my Sairam tried to do like just a deep learning model, but one of the problems we faced is the training was fine. Training ran pretty fast, but on the testing, he could only find a way to predict one case at a time. So we didn't find batch prediction. Batch prediction.
Oh, okay.
Yeah. That was a big. So it would say he wrote a loop, and it said it would take 100 hours, but we only had to finish in 8 hours.
Oh, I see.
And last, this link is really great, like because it compares all the XGBoost and Light GBM are still very popular for like all tabular data.
Yeah.
So let me share it. And I will send the notebook. I think I can make my Kaggle kernel public, and I will just put it here.
Oh, that'd be great. I'd love to have a look at that.
Okay, I just had to figure out how to make it public. Okay, that's all I have.
Okay, well, right, thank you so much. It was really great to hear from you on how successful Kaggle, and to know that we have successful Kagglers in our own group here. That's terrific.
Yeah, it's great.
Yeah, so
also shoot out to Sanyam in this regard. He also recently won a Kaggle competition.
That's right. We have 2 successful Kaggle groups in our little meetups. That's terrific. Okay, I think we've gone a little over, so let's end the meeting, and we'll see you all next week.
All right, that's great. Thanks, Joseph and Mehul. Thanks very much.
Yeah,
Thanks everybody. Yeah.
Thanks, guys.
Thank you.
Thanks, Tyron and Mehul.